Okay, so these are the notes for 5.1 where we're starting to solve systems of linear equations using two variables, meaning x and y. When we talk about a system of linear equations, we're talking about visually when two lines cross. We're also talking about when two equations are equal to each other. Or we call it sometimes a break-even point for sales, or at what point do two products cost the same, different things like that. Okay. And so we have two different forms of the equation. We have standard form, ax plus by equals c, where a, b, and c are numbers. Or we have slope-intercept y equals mx plus b, where m and b are numbers. In both of these, there's kind of a one versus another method for solving. Typically when we have it in standard form, we're going to use elimination to solve, and that's where we add two equations together and cancel out a variable. The other is slope-intercept. When we're here, we're going to typically look for substitution. That's a little bit more common. The other option is to graph it. Okay, so just looking at the format of the equations, that can sometimes give us an indication as to which method we should choose. To say that an ordered pair, like 4, -1 here, is a solution, means that the ordered pair has to be true in both equations. Like if I plug in 4 and -1, 4 plus 2 times -1, that'd be -2. 4 plus -2 is 2, and that's true. But it must also be true in the second equation. 4 minus 2 times -1, well, -1 times a -2 would be plus 2. 4 plus 2 is 6. Also true. So in this case, we would say that 4, -1 is a solution. If it's true in one of them and false in the other, like for instance if this 6 became an 8, then we would have to reject it because it wouldn't work. And so this would not be a solution to the system. System means that there's more than one. So one of the methods is to graph. Graphing is great because you can physically see the intersection. However, if you're using decimals, it's more complicated. So if the numbers turn out to not be whole numbers, that's a real challenge. Also, if you don't have a graphing calculator or graphing paper, getting the grid lines, getting everything to line up just perfectly can be hard. So typically we want to use technology or at least some formal graphing paper. Algebraic methods, there's a couple. We can solve anything algebraically or find out if there's a solution at least. But the problem with that is that sometimes when we do this algebraic approach, we still don't know what the picture looks like or where the lines are crossing. We know where they are, but what are they doing prior to crossing? One of the ways we can do this is by substitution. Whenever we have a variable that's easy to get alone, like this y is alone, we can say what it's equal to could replace it in the other equation, making 4x minus 3 times -x minus 1 equal 24. So now all I'd have to do is clean up via distribution. This would be 4x plus 3x plus 3 equals 24. This becomes 7x. I'm going to minus 3 equals 21. So x would equal 3. Now I need the y value. Well, in order to get the y value, all I have to do is take the x and plug it back into my substitution equation. So in this case, y, okay, sorry, that was me saying over here is y, is equal to negative x, which is 3, minus 1. Well, a -3 minus 1 is -4. So the answer is 3, -4. Did I have to graph it to find that? No. Now, I don't know much about the lines other than 1, 2, 3, 1, 2, 3, 4. There's the intersection. If I investigate a little bit, I know this line has a negative in front of the x. That's a slope that's negative, and so I can assume that that one is coming down like this. Sorry, I'm way off. There we go. Down like that. But other than that, that location is kind of hard to interpret very much. But it was easy because I didn't have to do any extra work. Then there are the systems we're going to do via elimination. Let's look at this second one. They don't line up quite right. I need to get the x's and y's together, so I'm going to subtract this over, and I'm going to add this one. What these equations are going to look like now would be 2x minus 7y equals -17, and 3x plus 5y equals 17. So the problem with this right now is if I combine them, neither the x nor the y is going to cancel. But if I times the top by 3 and times the bottom by negative 2, I would get 6x and negative 6x. So let's do that. I'll get 6x minus 21y equals negative 51. And then down here, I'll get negative 6x minus 10y equals negative 34. And that's through multiplying all the way through. The x's do cancel. I get negative 31y equals negative 85. And then just divide by negative 31. Now this is going to come out as a really weird decimal. And I'm going to stop here because we would just plug that decimal in to solve for x. Sorry about that. If we keep going, that y value would just come out of my calculator and I'd plug it back in to find x, and I'd be done. There are three different types of solutions, or three types of things that can happen. Two lines can intersect in one spot and have exactly one solution. Two lines can be parallel and never cross each other. If they never cross each other, then there'd be no solution. And then we can have two lines that are directly on top of each other. Whoops, sorry. You can imagine those being exactly on top of each other, and they cross infinitely many times. In those cases, we'll notice different things happen. For instance, when we do elimination or substitution, you'll end up with a true statement like 5 equals 5 or 0 equals 0, where no matter what you do, that's always true. That would be an infinitely many solutions. However, if you're solving and you end up with something weird like 6 equals 10, we know that's not true, and we would say that therefore the lines are parallel because they never cross. All right, well, good luck, and hopefully that helps you. See you in class.